Hi, everyone. My name is Yuke Wang. I'm the fifth-year PhD student at UCSB. Today, I would like to introduce our project, MGG, Accelerating Graph Neural Networks with Fine-Grained Intra-Kernel Communication-Computation Pipelining on multi-GPU platforms. Nowadays, graphs are everywhere, and GNN is the key to extract the valuable information from the graphs. We can easily find its appearance in a wide spectrum of application, including the analysis of the social networks, the control of power grid, the fault detection in financial service, and the molecular analysis in biology. So now let's dive deeper into the underlying mechanism of the graph neural networks. Specifically, from the operation view, graph neural networks combine the graph operation like the page rank to gather its neighbor embedding information and the neural network operation like the multi-layer perceptron to update the node itself. From the model perspective, a graph neural network interleaves execution of the GN layers and the normal NN layers, like the ReLU and the multi-layer perceptron. With the increasing size of the real-world graph data, the size of GN input graphs also scaling up. Specifically, there are two major trends. The first one is the graph structural scaling, which promotes the model generality, as shown in the huge number of the nodes and edges. For example, the recent dataset has reached to 100 million nodes with 1.6 billion edges. And the second direction for scaling is to enrich the node and edge properties, which aims to promote the efficiency of the downstream tasks, as shown by the size of embedding of each node shifts from the tens to hundreds or even thousands. For instance, the recent Ready dataset also has 600 input features. Meanwhile, at the same time with the scaling of these deep learning applications, the deep learning hardware infrastructure are also scaling its compute capacity and the memory capacity to catch up. On the left, we have a powerful single GPU like A100 or even H100 that's recently released by NVIDIA. In the middle, we have the multiple GPU on a single host, like the NVIDIA DGX baseboard, which allows the scaling a single application for larger input and models. And by looking into its details, we can summarize three of its key features. First, it offers the high memory compute and memory capacity to handle larger input. And second, it has a high bandwidth like the NVLinks to connect different GPU for efficient communication. And lastly, this kind of baseboard also serves as the building blocks for even larger clusters like the 13 clusters that rank very top on the top 500 list. Unfortunately, the powerful hardware cannot solve everything. The conventional single GPU solution for graph neural network scaling, like the DGO, it leverages the operator specialization for communication. It does not work well for the multi-GPU settings. Such a design features a separate communication and computation phases. As illustrated in the right figure, a graph with partitioned and distributed on two GPUs. It will firstly explicitly fetch the remote neighbors in the first phase, and then it leverages the existing single GPU kernels for computation. In this kind of cases, each node will first perform aggregation on its local neighbor and also its fetched neighbors. Compared to the dense and regular communication in the multi-GPU DNN training, communication in multi-GPU GNN features a fine-grained and irregular communication pattern that are yet to be optimized by any existing libraries, even like such as Nico or Honevoid. However, by using such design, we will encounter several weaknesses. Firstly, we will have a high individual neighbor access cost due to its random indexing and the fine-grained data movements. Secondly, it will have features high GPU idleness between the computation and communication phases due to the natural neighbor imbalance across nodes. On the other hand, there are some solutions that follows the traditional distributed graph processing scaling strategies. It also does not work well. This type of the solutions features the schedule transformation for dense communication, for example, like the neural graph and P3. And they count on existing libraries such as Nico or Honevoid to handle the communication. As exemplified in the left-hand side, we have two GPUs where the neighbor aggregation of each node are decomposed into three major phases, where the first phase performs the partial aggregation on the local neighbors, And the second phase is focusing on the swap of the neighbors between GPUs. And the last phase is perform the neighbors that are already fetched from the remote GPUs after the swap. With this kind of solution, we also encounter several weaknesses. Firstly, we have to perform additional algorithm-level transformation such that it can fit into this kind of coarse-grained and regular communication pattern. And secondly, there is a redundant data movement because we have an even coarse-grained communication between the GPUs. However, not all this kind of communication will be used in the later on computation. And lastly, we have a decreased computation efficiency due to the fact that computation are divided into multiple phases. The limitation of these solutions motivates us to explore the specialty of the GN computation paradigms and the hardware platform. The first observation are focusing on algorithm, which provides the new opportunity to fine-grained pipelining. As shown in the left-hand side, the neighbor embedding of the individual graph node are aggregated sequentially. And prior solutions over-approximate such dependencies through the coarse-grained communication and computation stages. However, we foresee more effective solutions through the fine-grained overlapping. Here, we explore a new design, as shown in the right. We have a node A in terms of its local access and the neighbor aggregation computation. And we also have the node B, which follows similar paradigms. By fine-grained overlapping, we overlap the computation and the memory access from A and B together, such that we can have a more dense execution pipelining. So here, we can amortize the communication cost by fine-grained overlapping of the neighbor aggregation from different nodes. The second observation will be focusing on the hardware architectural design. In the multi-GPU context, the stream processor on GPU can be multiplexed for operation for overlapping. The key to support this is that each GPU stream processor equips with many CUDA cores and some other function unit that can simultaneously support different operations. This includes the logical operation, the arithmetic operation, the remote access operation, and the local access operation. Such a design provides the essential gradients for pipelining, which is that communication and computation can co-run on the same unit at the same time to fulfill those idle GPU cycles. In a simple analogy, we list here, once we have a different stream processor perform different operations, we can treat it as the Coke vending machine, which we regularly say at the Costco. And with this kind of design, each stream processor as the vending machine, and each operation from different types can be treated as a different cup in different size. With all these observations, we introduced the MGG design for systematic scaling the GN computation. MGG takes the sparse and irregular GNN workloads and generates the fine-grained balanced pipeline for efficient execution on multi-GPU platforms. MGG consists of several major components, including the kernel runtime manager and the runtime parameter optimizer. And it also features the novel pipeline view and abstraction for hiding the communication latency, a GPU-tailored pipeline construction for tackling the input dynamicity, and the GPU-aware pipeline mapping for tackling the hardware diversity. And in this talk, we'll be mainly focusing on the runtime manager for pipeline construction and mapping. Our first key contribution is to create a new pipeline view and abstract for the multi-GPU GNNs. This contribution is to tackle the neighbor access latency for the remote neighbors. There are two major challenges. Firstly, the communication overweights the local computation and access, and they normally dominate the overall execution. Secondly, the communication exacerbates the already imbalanced workload. So our key insight to address this challenge is that the communication overhead actually can be offset by the fine-grained operation on the local GPU stream processor unit. As shown in the figure below, we remove the explicit barriers between the communication and the computation stage compared to the existing solution, and we co-schedule this operation from both stages holistically. With such new design, we can have several benefits. Firstly, the idle cycle of the GPU's communication can be fulfilled by the local computing. And secondly, the multi-GPU GN workload can be further abstracted as the fine-grained dynamic software pipeline. Here, we formalized our pipeline in 3 stages, where the first stage is load the remote neighbors, the second stage is load the local neighbors, and the final stage is perform the aggregate computation. And our key insight here is we prioritize the long execution operation to facilitate its overlapping with the shorter execution operation. Our second contribution is the pipeline-aware workload management, which tackles the input dynamicity in the multi-GPU GNN workloads. The key challenge here is that input diversity, such as the graph size and sparsity, could affect the pipeline efficiency, like the pipeline bubble ratios. Our key insight is that pipeline actually can be tailored for maximizing efficiency based on the insight from the GNN input. For example, we have a number of nodes, we have a number of edges, and the average degrees. Specifically, we build the pipeline and optimize through the heterogeneity and granularity-aware pipeline enhancement. This optimization is trying to facilitate a more balanced workload distribution among pipeline stages. And our key observation is that the cross-grain pipeline could hardly adapt diverse input. We therefore perform the partitioning of the existing workload and to make them into smaller chunks to facilitate the overlapping. For example, here we partition the labels into local and remote labels, and we set a constraint for each granularity. With this kind of design, we can get a further improve the pipeline with the better overlapping of different operations from the local and the remote labels. And such optimization improves the overall performance by 60 to 80%. Our second contribution is the GPU-aware pipeline mapping, which tackles the hardware diversity in the multi-GPU platform. This includes the GPU device diversity and also the GPU connection diversity. And the key challenge we address here is that hardware diversity, like the compute and the communication speed, would affect the pipeline execution performance, like the stream processor utilization and occupancy. And our insight is that dynamically configurable pipeline workload to stream processor mapping can maximize the pipeline execution performance. And our solution is to mix the originally separated local and remote workload and interleave them. So the first step is to interleave the local and remote workload, and we also set the configurable parameters like the interleaving distance to facilitate this step. And the second step is to map such a workload to the executable unit, like the GPU WAPs. And here we also provide the parameters like the workload to WAP mapping parameters to adjust their mapping strategy. And finally, we assign the individual WAPs to the stream processors for execution. So this is the last step, such that the actual pipeline can be executed on the GPU unit. Further optimization, including the intelligent runtime design and the specialized memory optimization and design, please refer to our details, or please refer to our papers. Now let's take a look at our evaluation. For data set, we cover the typical large data set that demands the multi-GPU collaboration. For GNN, we cover the graph neural network and also the graph GIN, graph isomorphism network. For evaluation platform, we cover the NVIDIA DGX A100. And for baseline, we compare with the DGL and our design with unified memory and also the rack system. Let's begin with the overall performance. Overall, our design achieved a 4.4 times speed up on average in comparison with DGL, and also 10 times speed up compared with ROC on the GC and GNN on average. The overall trend here is that our design demonstrates a higher speed up on larger and sparse graph compared to this baseline, which for this baseline, they generally suffer from the coarse-grained data movement and also the consistent GPU host involvement. And further, we apply our design with the existing the unified virtual memory. And our design achieved 4.8 times speed up compared with this design. This comparison indicates that the coarse-grained communication design, for example, that the unified memory could hardly hide the communication latency by overlapping itself with the local computation. And our additional analysis covers the label partitioning, and which demonstrate our optimization can offer a 2 times speed up, and also the workload interleaving to demonstrate the hardware diversity and achieve the 1.8 times speed up. In summary, our key focus and our key contribution can be illustrated in this way. Firstly, we exploiting the joint optimization of the communication and computation through our novel and unique multi-stage pipeline for the multi-GPU workload. Secondly, we capitalized our pipeline benefits for input dynamicity through our GN-tailored pipeline construction. And finally, we enhanced our pipeline efficiency for diverse hardware through our GPU-aware pipeline mapping. And that's all. Thank you for your listening. And if you have any questions, feel free to reach out to us through email and also check our code on the GitHub. Thanks.